to look at polycyclic aromatic hydrocarbons as interstellar catalysts and reactants. So you can see the addition, but you cannot really directly see.
So I've just delivered a keynote speech at this conference on nanocarbons in space in Edinburgh that I'm presently attending. The main topic of this lecture was the work we've been doing on a class of molecules called the polycyclic aromatic hydrocarbons. So you can think of them as small pieces of graphene, nano pieces of graphene cut out and terminated with hydrogen atoms at the edges. So here on Earth, the polycyclic aromatic hydrocarbons are mainly known as pollutants. They're one of the most dangerous constituents in the exhaust from diesel cars. They're known to be carcinogenic, so we really try to avoid them here on Earth. But in interstellar space, they may play a much more benign role as catalysts for the formation of other molecules. So interstellar space, the regions we are interested in are the regions where new stars and planets form, so interstellar dust and molecular clouds. And these regions are extremely cold, down to minus 263 degrees, 10 degrees above absolute zero. And also they are very sparse, so the gas is very sparse. It's actually what's referred to as ultra-high vacuum conditions. So with these very low pressures, very low temperatures, then it's a bit of a conundrum how you can form the different molecules that are actually observed in space. So far more than 300 different molecules have been observed, but how are they made? So the thought is that they must be catalyzed, their formation must be catalyzed by interstellar dust, but potentially also by these polycyclic aromatic hydrocarbon molecules. And what we have been investigating in my group for a long time is whether PAHs can catalyze, or polycyclic aromatic hydrocarbons can catalyze the formation of molecular hydrogen. And we've really been able to show that they do act as efficient catalysts for molecular hydrogen formation. So molecular hydrogen is the most abundant molecule in space, and it's also a key molecule for the formation of more complex molecules. So what we have shown is that hydrogens can add onto the polycyclic aromatic hydrocarbons, forming superhydrogenated polycyclic aromatic hydrocarbons, and then once the molecules are superhydrogenated, they can efficiently catalyze H2 formation. Not only that, if we start out with a molecule that already have, for example, oxygen atoms on, then we can also catalyze oxygen-containing molecules. We can also see that the hydrogenation leads to a breakup of the molecule so that we can form a whole series of different carbohydrate molecules via this route. And in this case, the pH is no longer just a catalyst, it's actually a reactant in these reactions. We've also seen that there's a higher possibility for these molecules to react with deuterium, the more heavy hydrogen isotope, than with hydrogen itself. And this, we still do not have a theoretical explanation for why we have this increased cross-section for reactions with deuterium. But interestingly, in new James Webb Space Telescope observation from Orion Bar, they're actually seeing that in regions where a lot of atomic hydrogen and deuterium, they do see a deuteration, so an excess of deuterium additions to the polycyclic aromatic hydrocarbons. And this may relate, or maybe our hope is that we will be able to explain these observations based on our experimental results. Beyond the pHs, I also talked about experiments we are doing to see whether we can create amino acids under these conditions, extremely low temperature, extremely low pressure conditions. And here we are also sending in hydrogen atoms onto the simplest amino acid, glycine, seeing whether we can activate it so that it will become reactive and open a pathway to form all of the other amino acids beyond glycine. Also talked a little bit about fatty acid formation. So can we start with an alkane chain and then add oxygen atoms onto this to form the fatty acids? So this is all activities that are part of our Center for Interstellar Catalysis, where we really aim to investigate whether the molecular building blocks of life, amino acids, DNA bases, fatty acids, and sugars, can form at the extremely low temperatures and pressures that we have in interstellar space. So can they form even before the formation of stars and planetary systems?